scientists have confirmed a form of water that is simultaneously solid and liquid. It is the latest advance in the study of water, a seemingly simple substance that can shift between many different configurations. That's a really strange state of matter, said Marius Millet, a physicist at Lawrence Livermore National Laboratory in California, the lead author of a paper published Monday in the journal Nature Physics that describes the experiments. This new form, called superionic water, consists of a rigid lattice of oxygen atoms through which positively charged hydrogen nuclei move. It is not known to exist naturally anywhere on Earth, but it may be bountiful farther out in the solar system, including in the mantles of Uranus and Neptune. Water is a simple molecule, two hydrogens attached to one oxygen. The three atoms normally form a V-shape. In the usual ice found on Earth, the verses connect in an airy structure. That is why water, unlike most every other substance, expands when it freezes. When squeezed, the hydrogens and oxygens shuffle into other crystal structures. Scientists now know of more than a dozen different forms of ice. Theorists first suggested 30 years ago that superionic water might exist under extremely high pressures and hot temperatures. The heat melts the chemical bonds between the hydrogen and oxygen atoms. The high pressure keeps the larger and heavier oxygen atoms stacked in a fixed crystal alignment, a solid, while the hydrogen nuclei, or ions, flow through, a liquid. That makes it a conductor of electricity like a metal, but the current is carried by positively charged ions instead of negatively charged electrons. Scientists believed that superionic water might be found in the mantles of Neptune, pictured, or Uranus, and could explain the lopsided magnetic fields of these planets. NASA It's as though the water ice is partially molten, said Raymond Jean-Loz, a professor of Earth and planetary science at the University of California, Berkeley, and an author of the Nature Physics paper. In the new experiment, scientists at Lawrence Livermore first squeezed water between two pieces of diamond with a pressure of 360,000 pounds per square inch. That is about 25,000 times greater than the air pressing against you here on the surface of Earth, and the water is squeezed into a type of ice known as Ice 7, which is about 60% denser than usual water, and solid at room temperature. Each diamond cell contained about 1/7 millionth of an ounce of water. The researchers then took the compressed ice, packed in carry-on luggage, to the University of Rochester where it was blasted by a pulse of laser light. That caused shock waves through the ice that lasted 10 to 20 billionths of a second, heating it to thousands of degrees and exerting a pressure more than 1,000,000 times that of Earth's atmosphere. Those conditions exist inside Uranus and Neptune and undoubtedly within numerous ice giants around other stars. Earlier experiments by other groups had produced conductive water that could have been superionic, but those scientists could not determine if the current were carried by ions and not electrons. Here, Drive, Millet and his colleagues were able to capture the optical appearance of the ice. If electrons were moving around, it would have been reflective. That is why metals are shiny. Instead, the sample was opaque. That pointed to the movement of ions instead, indicating a superionic ice. The superionic ice melted into a liquid at about 8,500 degrees Fahrenheit. It is a rather amazing experiment and the results are consistent with theoretical and computational predictions, said Roberto Carr, a chemistry professor at Princeton. The superionic ice could help explain the lopsided, off-center magnetic fields of Uranus and Neptune, the solar system's 7th and 8th planets that are known as ice giants and were visited briefly by NASA's Voyager 2 spacecraft in the 1980s. Instead of Earth's magnetic field generated at the core of the planet, the fields of those icy bodies may originate, in part, within shells of superionic ice inside their mantles. Dr. Jean-Loz said the agreement between experiment and prediction offered promise that scientists are beginning to understand the basic physics of how molecules in general behave under changing temperatures and pressures well enough for practical use. As one starts validating those kinds of predictions, it gives a hope that one could start thinking about engineering new materials. Dr. Jean-Loz said, where you tell me what properties you want, and someone can use a computer now to figure out what kind of material, what kind of elements you have to put together, and how they'd have to be packed together to come up with those properties. Dr. Carr, one of the scientists who have explored superionic ice in computer simulations, has suggested that there may be several types of superionic ice, with oxygen atoms rearranging in different crystal structures at even higher pressures. That will not be easy to test. But HES impressed that the theory has been tested at all. I'm always surprised by the ingenuity of the experimental people, in devising ways to both create the extreme conditions that produce something like superionic ice and the tricky measurements to verify the result, he said.